Hi, welcome back. I am Dr. Faiz Ahmed. Today we will be covering a vector algebra component form. So, so far we were discussing the vector in abstract form. So we don't have any coordinate system to express a vector. So it is time to define a coordinate system. Coordinate system is a reference system to express the vectors. We will start with a very simple one. And the simplest one is the Cartesian coordinate system. In Cartesian coordinate system, we can express any point in 3 dimension with in x, y, z form. So we have origin, reference origin, and then we can express any vector or point in 3 dimension in terms of x, y, z, where we have a point and we have a vector, some vector, arbitrary vector a. We can express this point or this vector in terms of 3 unit vectors x, y, z, and this point is x, y, z, and to express this arbitrary vector a, we need a is equal to some magnitude in x direction, which we are saying ax, x, then unit vector, some magnitude in y direction, and some magnitude in z direction. So any arbitrary vector in 3 dimension can be expressed the unit vector x, y, z, and the magnitude in that specific direction. And we say ax and ay and az are the components of vector a. So what actually ax, ay, and az are? Geometrically, they are in fact projections of a along x-axis, y-axis, and z-axis. So how we calculate the projections? So we used to calculate projection with the dot product. So ax is a dot x, ay is a dot y unit vector, and then az is a dot z unit vector. So any point in 3 dimension can be expressed in terms of vector a, where vector a has 3 components ax, ay, and az, and those are the projection of the point on these axes. So geometrically, we have again this, we have a point which is again a vector A, and the components are projection on the plane xy plane here, x, y, z. So projection on the xy plane so this length, or either this length, is ax, and the whole vector is ax x unit vector in this direction, and this is y, so this is ay y, which is projection on y-axis, and this height, which is z, is az, and the complete vector is az, z unit vector. So this is how we represent a vector in Cartesian coordinate system. So we can perform the vector operation similarly for in component forms. So we call this formulation a component form. So we represented a vector into its components, and if we want to add two vectors, say vector A and B, then they can be added ax x plus ay y plus az z plus bx x plus by y plus bz z. So we can add the components, gather the components of x unit vector, so it will become ax plus bx x plus ay by y plus az plus bz z. So similarly, we can define the dot products, and the dot products are, or before dot product, we can discuss the scalar multiplication. And we know the scalar multiplication is if we have a vector A and we have some alpha which is scalar, then alpha A will become simply alpha AX x unit vector plus alpha BX y plus alpha BZ AZ, sorry, AZ Z unit vector. So, and dot product, as in the coordinate system we define unit vector x, y, z. They are mutually perpendicular unit vectors, so their self dot products will be one and they are perpendicular, so their dot product with x with y, y with z, and with z with x, they all will be 0. So dot product of two vectors, a vector a and b, again a dot b is equal to axx plus ay y plus az z dotted with bx x plus by y plus bz z. So self dot product will be 1 and the dot product of x with y or z will be 0. So we will left with ax bx plus ay by plus az bz. All right, self dot product will be a dot a is equal to a square is equal to ax square plus ay square plus az square, and it implies a is equal to ax square plus ay square plus az square under root. All right, and similarly we can define the cross products, and the cross products will be self cross product will be 0 because they are again perpendicular to each other, not as we define this defined with the cross product is defined with the sine of theta, and self cross product mean their angle will be 0 to each other and sine 0 will be 0. So z cross z is equal to 0, and x cross y is equal to y cross x is equal to z unit vector. Similarly, y cross z is equal to minus z cross y, as we discussed that when we change the direction, then we saw the thumb was going up or down, so we have to place a negative sign to accommodate the sign. So a negative sign will come with excuse me with x unit vector. So z cross x is equal to x cross z, a negative sign here again, is equal to y unit vector. And usually I used to remember using a anti-clockwise circle. So we have x here, y here, and z here. So if we are going to take cross product of x and y, so it's z, and if I am going to take y cross x, then I used to put if I use clockwise direction, then I used to put a negative sign with z when I take the cross product, and same goes x cross y z, y cross z x, z cross x y. And if I go the other way around, z cross y is minus x, y cross x is minus z, x cross z is minus y. So if I go clockwise, then I put a negative sign, and if I go anti-clockwise, then I use a positive sign. So we have we can define the cross product between two vectors, a cross b, and again in component form. So we have to write ax x plus ay y plus az z cross with bx x plus by y plus bz. So cross, we have to take cross with every quantity. If we take cross with x cross x, it will become 0. X cross y will become z. X cross z will become y. So doing all the math, we will come up with something like this. Bz minus az by with unit vector x, then plus az bx minus ax bz y unit vector plus ax by minus ay bx z. So there is another way to find the cross product, and that's called the determinant method or the determinant form. And I found it easiest compared to remember all this or to perform the cross product using this all. So in determinant form, we have to put x, y, z unit vectors here. Then we have to put ax, ay, az, bx, by, bz, the corresponding components into the for A in the second row and for B in the third row. And determinant, we know how to find determinant. We have to take x and then leave this row and this column and multiply the remaining one, this one and this one. So it will become ay bz minus by az. Then we have to plus minus 1 of 1. Here in fact it was minus 1 of 0. And we have to take y, and then we have to solve. We have to leave this row, this column and this row. Then we have left with this and this terms. So we have to compute these two terms and put there and so on for the third one. So I used to find it easy to compute the cross product as compared to the using the other method we were using. All right, we have an example to solve. We have example 1.2, and we have two vectors. Vector A is equal to 1x plus 0 y plus 1 z. and we have other vector b. Vector b is 0x plus 1y plus 1z, and these are the diagonal of our cube faces. So if we draw and we are asked to find the angle between these two vectors, or these two diagonals of a cube. So in fact, if I try to draw a cube and draw these two vectors, so we have this vector should be there, not here. X, Y, Z. So this is cube, and these are the two faces, face diagonals of the cube, and we have one X and one Z. So the first diagonal is this one. This is vector A, and we have one Y and one Z. So this will go here. So this is vector B. So we have to find angle between these two, and this is theta. And we can find using the dot product. If we compute a dot product A dot B, it will become taking the dot of A and B, 1.0 plus 0.1 plus 1.1 is equal to 1, and other A dot B, the definition of the dot product is AB cosine of theta. So we need to find A magnitude, which is, we are saying A, it is under root 2. We have to find B magnitude, vector B magnitude. This is equal to under root 2, and we know the dot product is 1. So A dot B is equal to under root 2 value of A, value of B, cosine of theta, and A dot B is 1. So this will become under root 2 multiply, then it turned 2 cosine of theta is equal to 1. So cosine of theta will become 1 by 2, and theta is cosine inverse of 1 by 2. So if you use calculator, you will find that this angle is 60 degree. So we found theta is 60 degree between the two diagonals, and if you measure this angle by any scale, then you will come up with the same number. So you can use the definition of the dot product to find the angle between two diagonals of a cube. We will continue with the next section in next lecture.